everybody. Today we are going to be talking about concentration. I want to go ahead and say pull out something you can take notes on. If you're taking your notes on your computer or a piece of paper, I highly recommend taking notes during this video lesson because these notes are going to be very important moving forward during the unit. So I'm going to give you a moment here to get out a piece of paper or to open up a tab that you're taking notes in. We're going to talk about different concentrations today, so I'll give you a moment to take care of that before we move forward. All right, if that wasn't enough time for you, go ahead and pause the video here and get out your something to take notes with. Otherwise, we're going to move forward here in talking about different concentrations. This is a math-heavy lesson, so I want you to grab a calculator. You're going to need a calculator for this lesson. So go ahead and go grab a calculator. Pause your video now while you go grab a calculator. All right, good. So we've got our calculators. We're ready to do some math. We're ready to learn, take some notes in the process here. We're talking about different concentrations. We know when we were talking about some solubilities and how some things are dissolved in others, you're going to want to know the concentration. If we refer back to something like sweet tea, you want to know how much sugar is in your sweet tea, the concentration of sugar as it relates to the tea or the water. So we're going to be able to do some calculations with that to kind of figure out what concentrations of different solutions are going to be. The first thing we need to discuss is how to convert from milliliters to liters and grams to kilograms. This is something we've discussed already, so it shouldn't be new to you. We've talked about it in 2 different units, but I do want to review this to get your mind thinking about how to convert from milliliters to liters and grams to kilograms. The first thing we need to do in converting from milliliters to liters is remember that there are 1,000 milliliters for every 1 liter of a solution, or vice versa, you have 1/1000th liters per every milliliter within a solution. So that's important to remember. We're going to try to stick to, in our conversions, only going from milliliters to liters, but I still wanted to bring up how you go from liters to milliliters. And we're going to work a problem here in a second on how to convert from one to another, just to get your mind remembering how to do that. The other thing we need to remember is that there are 1,000 grams in a kilogram of a substance, or if you go the other direction, there is 1/1000th kilogram per gram of a substance. So again, we're going to try going only from milliliters to liters or grams to kilograms in this unit. I'm not trying to give you too much math to worry about here in both directions. So really try to hone in on remembering how to go from milliliters to liters or grams to kilogram. I'm going to give you 2 practice problems here. First, I want you to convert 13.4 liters into milliliters, and then try to convert 3,200 grams into kilograms. And do this in your notes. You'll put your answer on the Ed Puzzle video to check for correctness. But see if you can convert from 13.4 liters to milliliters and convert from 3,200 grams to kilograms. I'll give you a moment to do both of those, and then we'll check our answer and make sure we know how to do that. All right, so if we are converting from 13.4 liters to milliliters, this is where we use that T-chart, that factor label technique. So we have our T-chart here. The thing that we're starting with, the 13.4 liters in the question, that's going to go in the top left of our T-chart. We're solving 4 milliliters. That goes in the top right. We know from the notes here that there are 1,000 milliliters per every 1 liter. So if we set the chart up like this, we multiply everything on the top, we divide by everything on the bottom. So we would do 13.4 liters times 1,000 milliliters divided by 1. So converting 13.4 liters to milliliters would give you 13,400 milliliters. And then for our second question, converting 3,200 grams to kilograms, again, we'll set up our T-chart. What we start with goes in the top left. what we're trying to get goes in the top right. So we're starting with 3,200 grams. We're going to kilograms. So in the top right, we're going to have our kilograms. And we know our conversion is for every 1 kilogram, we have 1,000 grams. You can see that in the notes section right here, 1 per 1,000. So we would do 3,200 times 1 divided by 1,000. So if we're converting 3,200 grams to kilograms, that would give us 3.2 kilograms. And by the way, if at any time you're struggling on one of these topics, one of these math equations that we're working on, we've got quite a few more different math equations we're working through today, just write somewhere in your notes or shoot me an email and let me know that you're struggling with that specific topic, so that when you see me in class next, we can discuss it further and I can make sure you're understanding it. But for now, make sure it's in your notes, that you understand how to do this. And we'll move forward into a little more complicated mathematics here. So we get to talk about molarity. We're going to talk about another thing that sounds very similar to molarity in the same lesson. So I don't want you to confuse molarity with this other thing. So we're starting with molarity. And molarity is going to express the solute's concentration in terms of moles per liter. That's very important what terms it's in. We're doing moles per liter, or moles divided by liters. Notice it's liters here. It's not milliliters, it's not grams, it's not kilograms. It's moles divided by liters. Our equation for this is capital M, and capital M represents molarity. Remember, that is a capital M. So our molarity equals our moles of our solute divided by the liters of our total solution. Moles of solute divided by liters of the solution, of the total solution. So it's moles per liter for molarity. We can work an example problem here. I want to see if you can try to solve it, and then we're going to work it out together and see if we can figure it out. So we're going to calculate the molarity of a solution that contains 0.225 moles of sodium chloride in a volume of 2.8 liters. So I've given you the moles, I've given you the liters, and you have to calculate the molarity. So I'll give you a couple of minutes here to see if you can solve this question, and then you'll put your answer in the Ed puzzle, and then we'll work through it together to see, make sure that you get it correct. All right, so we've had plenty of time to work through this question. Hopefully you got it correct, but we're going to go through the steps here. Our first step, we want to write out what our variables are. We know we're looking for molarity because it says calculate the molarity. So our big M, our capital M, is unknown. Our moles in the question, 0.225, and our volume in the question is 2.8 liters. All of that's given to us. So what we do is we just plug it into this equation, moles divided by liters. So molarity equals 0.225 divided by 2.8. That's all we do here. And if you plug that in your calculator, you should get 0.0804 molarity. Your unit is called molarity here. Or you could say moles per liter. I would accept that on a test. And if you rounded your answer differently and you got 0.0805 or 0.08044, things like that, that's all acceptable here. I just rounded mine a little differently, but your answer should be 0.0804. All right, so that is an example on how to solve molarity. I'm going to give you a practice problem now to see if you can come up with the molarity of this solution. So I want you to calculate the molarity of a solution that contains 5.10 moles of sodium chloride in a volume of 175 milliliters. So go ahead and take a moment, see if you can figure that out, and then we'll work through some hints and solve it together. All right, so I've given you plenty of time here. We want to notice the units inside of this question before we really dive deep into how to solve this question. So our first step is to convert the volume from milliliters to liters. That's going to be the thing I feel like that trips most of you up if you were to get this question wrong. Because molarity's units are moles per liter. So we have to have our milliliters turned into liters before we can do any of the math here. So if we're converting the volume from milliliters to liters first, then we're going to list our variables. We'll solve the question. Pretty straightforward. So if we're converting from milliliters to liters, we're going to do our T-chart. And in our T-chart, what we're starting with is 175 milliliters. And that's what's given to you in the question. What we are trying to solve for is our liters. We're trying to convert it to liters. And we know that there are 1,000 milliliters per 1 liter. So we put the 1 on top, 1,000 on the bottom. 175 times 1 divided by 1,000 gives you 0.175. So that's your total number of liters. Now that we have our liters, we'll be able to list it with our variables and then solve the equation for molarity. So we're solving for molarity. We'll give it the question mark here. We know our moles in the question is 5.10. I should have given it the unit moles there, but I guess it works. And then our liters, our volume is 0.175 liters. Again, it needs to be in liters, not in milliliters for molarity. Then if we plug these in, it's 5.10 divided by 0.175. If you plug that in your calculator, I got 29.14 molarity. And that's that big M, the capital M. So we have to convert milliliters to liters for molarity. Make sure you list your variables, and then you just plug into the equation and solve. Again, if this particular type of question does not make sense to you, you're struggling with it, note that in your notes, or if you want to send me an email, and we can talk about that the next time you see me, to make sure you understand how to solve the math in these kinds of questions. So we've done molarity. Our next one is molality. So we did molarity. Now we get to talk about molality. So molality is different from molarity in that it expresses the solute's concentration in terms of moles per kilogram. So this time we're dividing moles by kilograms instead of liters. So molarity deals with moles per liter. Molality deals with moles per kilogram. Notice also the symbol I have here for molality, and that's going to be important here. Molarity is a capital M, molality is a lowercase m. So if you're trying to figure out what units to put, or you're given units in a question and you don't know if it represents molarity or molality, molarity is a capital M, molality is a lowercase m. Yes, there is an equation for molality. It equals the moles of your solute divided by the kilograms of your solvent. So molality is moles of solute divided by the kilograms of solvent. We'll work this example equation out. Calculate the molality of a solution that contains 5.10 moles of sodium chloride in a solvent that weighs 1.20 kilograms. So I've given you moles, I've given you kilograms, and I'm asking you to solve for molality using that equation. So I'll give you a couple minutes here, see if you can come up with the molality of this solution. All right, so I hope you put your answer in the Edpuzzle. I'll show you how to solve it. First, we list out our variables. M is our molality. We don't know that. Moles is given in the question. That's 5.10, and kilograms is also given in the question, which is 1.20. So mathematically, we do 5.10 divided by 1.20. If you plug that in the calculator correctly, you should get 4.25 moles. And if this doesn't make sense to you, then go ahead and write that in your notes that you need to, say something to me, and we'll work out some extra problems on this to make sure you understand the math. Or you can send me an email and say, I don't get it. And I'll be happy to kind of go through that more with you and make sure you understand it. We do have another practice problem with this. I want you to calculate the molality of a solution that contains 5.10 moles of sodium chloride in a solvent that weighs 375 grams. So I'll give you a couple minutes here. See if you can solve the molality of this particular solution. All right, so let's work through the steps. Let's see what we have to do. The first thing we need to identify is our mass when we're solving molality must be in kilograms in order to do the math correctly. And the question gives it to you in grams. So you have to convert the mass of the solvent to kilograms first. Once we convert it to kilograms, we'll be able to list our variables, and then we'll be able to solve the question. So if we are converting from grams to kilograms, we'll do our T-chart or factor label. In the top left of that, we have 375 grams. And we are converting to kilograms, so we're trying to find kilograms. We know our conversion factor is that there are 1,000 grams in every 1 kilogram. So we would do 375 times 1 divided by 1,000, which should give you 0.375 kilograms. So our mass of solvent is 0.375 kilograms. Now we can move on to our second step of this, which is listing our variables. We don't know the molality, that's what it's asking us for. We know the moles. The moles are in the question, 5.10, and our kilograms are also what we just solved for, so that's 0.375 kilograms. If we plug those in, 5.10 divided by 0.375 should give us a molality of 13.6. So our molality is 13.6 here. And that tells us the moles per kilogram. So molality is per kilogram, molarity is per liter. That's really important to differentiate, or you might not be getting questions correct on the homework or on your quizzes or tests. All right, next we are going to do calculations for parts per million, or ppm. ppm, or parts per million, is a way to express very dilute concentrations of substances. So something is so dilute, and by dilute it's just like watered down to an extent that we're using lots and lots of decimal points. Usually it's easier to express that by ppm, or parts per million. So we have the term percent, and cent in Latin refers to 100. So per 100 is a percent. So ppm is per 1 million. So in percents, when we solve for percents, we know we multiply by 100. So when we're doing per million, we'll be multiplying by 1 million in this equation. So our equation is our mass of solute. So we'll have to figure out what our solute is, divided by the mass of the entire solution. That's very important, mass of the entire solution. We're not dealing with solvents this time. We want the whole solution there. When we do that division, we'll multiply it by 1 million, and that will give us our ppm. So here is your example question. What is the concentration of a solution in ppm if 0.02 grams of sodium chloride is dissolved in 1,000 grams of solution. We don't know the solution, just solution. And that's the total solution. So go ahead and solve that. And we'll see if you get it correct. We'll work through the steps here. So take a minute, see if you can solve the concentration in ppm here. All right, so we want to write out the mass of our solute, which is given to us. Our solute is NaCl, or sodium chloride. It is 0.02 grams. The mass of our solution is 1,000 grams. That's also given to us in the question. So we do 0.02 divided by 1,000, and then we'll multiply that by 1,000,000 to give us our ppm. So you should get 20 ppm when you do 0.02 divided by 1,000 times 1,000,000. So notice when you do the 0.02 divided by 1,000, you should get a really small number. So this is a super dilute substance, and ppm expresses very dilute substances. So since our number is so small in that division, it's only logical that we multiply it by 1,000,000 to give us the ppm. So that's the reason people will use ppm for various solutions. I'll give you a practice problem here. So if you have 0.025 grams of lead nitrate, and that is dissolved in 100 grams of water, what is the concentration of the resulting solution in ppm? So go ahead and take a moment to try to solve this one, and then we'll work through it together and see if you got the right answer. All right, so I'll give you a hint here. We'll start with our steps. Our first step is you want to identify what the solute and the solvent are. Then we're going to combine the mass of the solute and the solvent to get the mass of the whole solution. And I'll explain that in a little more detail here in just a second. Once we've done step 2, we'll list our variables, and then we'll solve our equation. So our first step, identify the solute and the solvent. Our solute, 0.025 grams of lead nitrate. Our solvent, 100 grams of H2O. So our solute's the thing that's being dissolved. Our solvent is the thing that's dissolving. Then we need to combine the mass of the solute and solvent to get the mass of the whole solution. So I went ahead and kind of combined steps 2 and 3 here. So our mass of our solute is 0.025 grams. The mass of our solvent is 100 plus 0.025 grams. Because when we're doing this, we want the mass of the whole solution. So if we're doing the mass of the whole solution, it's not just the liquid. It's the liquid plus whatever solute you put in there. So our liquid is 100 grams of water. Our solute is 0.025. So 100 plus 0.025 is 100.025. Then if we do the math, we get 0.025 divided by 100.025 times 1,000,000. In this case, we get 249.9 parts per million. So our ppm here is 249.9. Again, if we're adding small, minute steps to these questions, you have to look for if I've given you the entire mass of the solution, or if you have to combine your solvent with your solute to get the total mass of the solution. In this case, I've just told you what your solvent is, and I've told you what your solute is. And you have to combine those two to get the mass of the entire solution before you can do the math. That's probably the confusing part on this one. And again, if you don't understand how to work this particular question or this style of question, make a note of it or send me an email. Then when I see you again the next day, you can let me know and we can work through some together to make sure you understand how to solve ppm. All right, our next questions deal with percent composition of a solute. Now, we dealt with percent composition during Unit 5 when we were doing percent yields. This is very similar to like a percent yield question. So this is kind of comes out of that unit with a little twist because we're dealing with solutes, solvents, and whole solutions this time. We're doing percents, not parts per million, so our multiplication will be a little different. So our percent composition is going of a solute tells you how much of a solution is made up of that solute. So if we're talking about sweet tea, your percent composition of sugar tells you how much sugar makes up the entire batch of sweet tea. We do get the equation. Our percent composition equals the mass of our solute divided by the mass of the entire solution times 100. Again, notice we have mass of solute and mass of entire solution. We're dividing by the mass of the entire solution. So sometimes I'll tell you what the mass of the entire solution is. Sometimes you have to figure that out yourself by adding together your solvent and your solute. So let's work through a question together here. A 4-gram sugar cube is dissolved in 341.25 grams of water. What is the percent composition of the solute in the solution? So I'll give you a couple of moments to try to work through this one, see if you can figure it out using that equation, and then we'll see if you're correct. We'll move on. All right, so the first thing we need to notice here is that we have our solute and our solvent. If we're looking at our solute, it's 4 grams because sugar is getting dissolved in water. And then our solvent is that water, but we don't use the solvent in our equation. If you look here at our equation, it's the mass of the entire solution. I haven't given you that mass in the question. I've only given you the mass of the sugar and the mass of the water. So you will have to combine those to get the mass of the solution here. So to combine those, you do 4 plus 341.25. So the mass of our entire solution here is 345.25 grams. Now we'll put that in our little equation here. So our percent equals 4 divided by 345.25 times 100, which gives us 1.16% sugar. So this solution of sugar water only has 1.16% sugar. The rest of it's water. That's what percent composition is telling us. All right, we got another example, another practice problem here for you to try working out. We have a solution prepared by dissolving 25 grams of sugar into 100 grams of water. What is the percent mass of the solute in the solution? So again, another percent composition question. Try to work this one out and see if you can figure it out, and then we'll work through it together. All right, cool. So let's list our steps. Our first step, we need to identify the solute and the solvent. Our second step, we're going to combine the mass of the solute and the solvent to get the mass of the whole solution. Our third step, we'll list out our variables, and then we're going to solve it. So our solute is the thing that is dissolving. 25 grams of sugar is dissolving. What dissolves the sugar? Our solvent, which is 100 grams of water. So we have our solute and we have our solvent. Moving on to step 2, we see the question doesn't tell us the mass of the entire solution. We're going to have to deduce that ourselves. So I've kind of combined steps 2 and 3 here again. So our mass of our solute, 25 grams. Our mass of our entire solution would be our solute plus our solvent. So 25 grams for our solute, 100 grams for our solvent. 25 plus 100 means that the mass of our entire solution is 125 grams. Then to do the percent composition math, you would do 25 divided by 125 times 100. So in this case, our percent composition is 20%. So there's 20% sugar in this solution. So it's probably a pretty sweet water. It's probably like you're drinking some Kool-Aid or something. So that is how you solve percent compositions. So we've worked through 4 different math types today. We've gone through molarity, molality, parts per million, and percent composition. And it's really important, remember, to differentiate molarity and molality, both by molarity using liters in its math question, while molality uses kilograms in its math equation. And then also differentiate between the letter used to represent molarity and molality. Molarity uses that capital M. Molality uses the lowercase m. So there's a big difference between molarity and molality, and those two get confused a lot. And then just remember, between parts per million and percent composition, parts per million multiplies by 1 million, percent composition multiplies by 100, but essentially it's the same concept. And you also need to always check when you're solving for percent composition and parts per million if the question gives you the mass of the entire solution, or if you have to deduce that by adding the mass of your solute with the mass of your solvent. So those are the big takeaways here. As you work through an assignment on this, make sure you're kind of following those cues to get the correct molarity, molality, parts per million, and percent composition. And again, if you have any questions on how to solve any of these types of questions, molarity, molality, percent composition, or parts per million, just jot it down in your notes so that we can talk about it next time you see me, or you can shoot me an email if it can't wait, and we can. I'll check my email at the end of the day, and we can discuss it to make sure you understand how to solve all of these math questions. I know this presentation was very dense on math, but it is kind of important moving forward in chemistry to get the correct concentrations of solutions, so that you aren't using too strong of a solution or too weak of a solution in things like cleaners, or even if you're making sweet tea at home or something.